Let's continue our journey of business then, and we're going to look at sampling today. What were basenets? It was a representation that allowed us to represent probability distributions over large sets of random variables by having a directed acyclic graph. And for each node in the graph, which would correspond to a random variable, we have a conditional probability table. That table stores the conditional distribution of that particular variable given its parents. Implicitly, you're encoding the full joint distribution. It's just a more effective way of doing so. And the way you get back the full joint is with this equation over here. You multiply all conditional probability tables together. That's what gives you the full joint. Here is the canonical example, the alarm network, 5 random variables with 5 conditional probability tables. Remember, the biggest one is always going to be the one for the variable here with the most parents. And if you want to compute the joint entry here, the entry of the joint distribution for plus b minus e plus a minus j plus m, you just look at each of these 5 tables and look at the corresponding entry in those 5 tables. And so you take those, multiply them together, you get your probability entry in the full joint distribution. We said rather than first blowing things up by alternate joining tables together and eliminating variables. By once you have joined all the tables, not first join and you end up losing a particular variable. Always join all the tables that have that variable together. And so variable elimination, sum it out and keep going. Now, what was nice about it is that then maybe you wouldn't have to build a full joint distribution and things would work out computationally more efficiently. The main work is building these factors as you join tables together and then sum out the variable. If you have a factor over k variables and they have domain sizes d, that factor has d to the k entries. So you want to somehow find a sequence of elimination of variables such that small factors along the way. Sharing a big factor is your major cost. We saw with this example over here that if you started with eliminating z and then only a very big factor right up front, very expensive computationally. If instead you eliminated all the x's first and then only as the last thing, you end up with a much more computationally effective variable. It's really important to run a variable elimination in the correct ordering for your basenet. How do you find the correct ordering? You could run search. That's one way to find the best ordering. Still a big search problem. So it's the one that you just work out pretty well. The worst case is that even the best ordering gives you large factors. I'm going to prove that to you right now. So we're looking at a special basenet here. What is this basenet encoding? This basenet is encoding into a fraction problem. The special fraction problem is called preset. What does that look like? It's a CSP where we have n's over a bunch of clauses. And each of these clauses involves 3 variables. A single clause over 3 variables is an or clause. X1 or X2 or not X3. Not X1 or X3 or not X4, and so forth. CSP, NP complete. What that means is that despite many trials of many intelligent people around the world to solve this efficiently, nobody has succeeded at it. These types of problems are just, there are no efficient algorithms to solve them. What I'm going to do now is show to you that if you can do you can efficiently solve these CSP. By showing that if you most likely efficient or such an algorithm just doesn't exist. So how do we encode this problem as a basenet? Well, the variables x1 through x7 are listed at the top here. Then I'm introducing additional variables. The variables y1 through y8 correspond to each of the clauses. So this first clause here is y1. Second clause, we have y2. And so what this CPT here is encoding for y1 is that y1 is equal to x1 or x2 or not x3. It's a very special CPT. Most entries are 0, some of them are 1. That's the idea. Then y2, same thing, and so forth. I should take that back. Most entries are 1, some of them are 0 for all of these. So that's our y variables in this second layer. And in the third layer here, we take the end of these two expressions, and that's y1, 2. Here we have y3, y4, and the end is y3, 4, and so forth. So we're just doing the end. You can say, why don't we end everything together at once? If you end everything together at once, you end up having a variable with a lot of parents. I want to show to you that I can represent the complete satisfaction problem by a big. So we do this end over all 8 clauses in a staggered way. Here, y1, y2, y3, y4, y5, y6, 7, and 8. And then here we have 1, 2, 3, 4 by combining 1, 2, and 3, 4. Similarly here for 5, 6, 7, 8. And then finally we have z, which as a meaning is just the end of y1 through y8. Variable has at most 3 parents in this basenet. So what that means is that this basenet, because every variable has at most 3 parents, small amount. Now, what happens if we run inference in this basenet? Let's say I ask you to answer the query P, Z. What is the distribution for Z? And let's say you have an answer. I'll tell you one more thing. I've told you what all the y variables are. The x variables have CPTs that are regular marginal distributions, and it's 0.5 for 0 and 0.5 for 1. So 50-50 in the x variable. What is the distribution for Z? And I can look at that distribution, and if I find that P Z equals 1, bigger than 0 implies satisfiable. Means that this constraint satisfaction problem actually an if and only if. If it is satisfiable, then there will be some non-zero probability for Z to become the value of 1. Why? All combinations have non-zero probability, and so one of these combinations is to Z having non-zero probability of 1. If you can even approximately answer this query of finding the distribution, accurate enough way to determine the probability of Z. If you can determine just the answer to this query over here, whether that's true or false, then you know whether that constraint satisfaction problem has a solution or not. If you can run exact inference in a basenet efficiently, you have solved the problem nobody else before, which is any questions about that? We say, well, we're not going to be hoping here that we can find a good order for all business when we do variable evaluation, because if we do that and find a if it's a CSP business in general, you're not going to be too lucky. So we have to resort to other things. One thing that I want to say before we resort to remember in CSPs about if you had a tree structured CSP, you can solve it very efficiently. If you're given a business that has a tree structure, it's typically called a polytree. Direction of the edges, you have a tree. Then there always exists a ordering of the variables such that you will not generate more numbers. And you should think about that, draw out a couple of well, is it true that I you have the same extension as we saw in CSPs. That is, if you have a non-tree structured business, take out some variables, give some value, run inference in the remaining, and of course have an outer loop that loops over all values of the variables that you took out, and do inference in potential failure. You find out from the result over here that if you variables to make your base in general, the number of variables to pull out of your business graph is going to be relatively large. All right, any questions about that? Yes. Okay, that's a good point. So business don't have directed cycles, but they do have cycles. So business that looks like this doesn't have a directed cycle, but it does have a cycle. Any other questions about this? So, and what we're going to do for the remainder of the lecture is just nobody else has time. Instead, we're going to give up on that for now, and we're going to at least it's fast. And if we spend more time, it'll get more and more accurate. So, sampling. Sampling is a lot like simulation. So, one thing you can have in your head is predicting the weather, interaction of pressure and so forth. Basketball games, you can think of how the game goes back and forth, and you simulate, like maybe someone scores on one side, maybe not on the other side, and so forth. And you could simulate what based on probability to make it back or not at any given time. That's really the core of sampling, is that you simulate a process and see what the outcome is, and then you repeat that. And you do that many, many times, and then you can start putting statistics on these results. So basic idea is you draw n samples from your sampling distribution. Then you compute an approximate posterior probability from these samples. In the basketball game, you maybe simulate the game 100 times, and then you say how many times did the Lakers win, and that would be your estimate of a probability. And then you can actually show that if you were to simulate sufficiently often, you would get the right answer. Sufficiently often, but if you're willing to. Why would you want to sample? Well, because exact inference is not possible in general, so we'll need to do something else. Why would sampling stepping through Let's do an example, very simple example of sampling. Step 1 is you get a sample U from a uniform distribution over 0, 1. For example, just a random call in Python. Step 2 is to convert this sample U into an outcome for the given distribution by having each outcome associated with a subinterval of 0, 1 with a subinterval size equal to probability of the outcome. What does that look like? This is your distribution. You now associate with your distribution parts of the 0, 1 interval, right? This will take up a 0.6 chunk, this will take up a 0.1 chunk, and this will take up a 0.3 chunk, and together that fills up the entire 0, 1 interval. So this is one way of doing this. You have many ways of doing this. This is just one choice. And if your random returns U equals 0.83, you just check, you say, oh, that's between 0.7 and 1, so I'm going to generate blue for this sample. You sample 8 times, maybe you get something like this, and now you could say something like, on the average, if a sample, well, not on the average, now you could estimate from this here, you could say, what is the probability of sampling red? You would say 0.5. Actually, no, because there are not 10 blocks. You would say 5 over 8. You say probability for red is 5 over 8. Probability for blue is 2 over 8. And probability for green is 1 over 8. These are approximate, but that's what you would estimate from these samples. So that's the basic building block, sampling from one distribution. Note that you can do the same thing if this is a conditional distribution. If this was a distribution for C given x equal plus x, let's say, and that was given in here, then if you knew x was equal to plus x, okay, now we'll look at sampling in base nets. We know how sampling works in general, but so far the only way you can sample what we are seeing so far is that you would just build the full distribution and then sample. We want to do something a little more clever than that. Here's prior sampling. All the metaphors here will be where the robots are sampling shapes and colors, so it's sampling a two-dimensional distribution. We're trying to get some answer to some probability query. All right, so we're sampling, and in this case here we have a base net, and we want to generate a sample. How do we generate a sample from a base net? We start at the top of the base net. What does that mean? You look at the directed acyclic graph, and you linearize it. You pick an ordering that's consistent with the partial ordering of the graph. So definitely C would be first. You sample from C. Somehow you generate a random number in 0, 1, and then accordingly, in this case it was between 0 and 0.5, and you found positive C cloudy. At this point, depending on how you linearize, you'll proceed with S or R. We proceeded with S. For C, we already have plus C, so this part of the table is now relevant. We sample a random number in the 0, 1 interval, then map it to plus S or minus S, depending on where we landed. Our example found minus S. Then we pick value for R, so we have plus C already, so this part of the table is relevant. Sample value within 0, 1 at random. Correspondingly, in this case, it was plus R. Now we can move on to the last variable, W. We have, as its parents, S and R. We have minus S and plus R, so that's where we're going to look. We sample from the 0, 1 interval, accordingly pick the W value, in this case, plus W. That's the procedure. So we don't have to build a full joint distribution to sample from the base net. We can do it one variable at a time. And this is our first sample. You can now repeat this, build up more samples. And what you see here is that despite that we deal with a lot of random variables, we never get this blow up that we would get with variable elimination. We get a procedure that's the number of variables that we have in our base net. Yes? What does that do? Now you can start answering queries. So somebody might say, what is the probability of plus S given plus W. And if these were your only two samples, you would then say plus W is here and here. Whenever there's plus W, half the time there is plus S. So I estimate this as 0.5. So that's an answer to a probabilistic inference query that we could have done and solved with variable elimination, especially for a toy example like this, but now we've solved it with sampling. It could be any type of query. Any of the queries we answered with variable elimination, you get answers based on looking at these samples and accordingly taking the empirical counts for the variables that participate in the query, and then answer the query that way. It'll be approximate, but it's very efficient. Yes?
So we do this with known base then, right?
Yes, you do it with known base, absolutely. That's far in the future, not today or the next. All right, that's prior sampling. Here's the algorithm. You get one sample out, you loop over all variables in your basenet in an ordering consistent with the directed acyclic graph. You sample xi from the distribution of xi given its parents. Because you sample in this particular ordering that's consistent with the graph, you will always already have sampled the parents of a variable before you try to sample the variable. So this works out nicely. Okay, do we get the right distribution over samples is something we need to verify. So let's say you follow this process. What is the probability of generating the sample x1 through xn? Well, that's the product of the probabilities of generating x1, then x2, then x3, and so forth until xn. For each one of those, the probability of generating a particular sample is this expression over here. Multiplying them all together, we get what is the original full joint distribution of the base net. So we see here in this equation that by sampling with this, the probability of having a sample is equal to the probability of that sample in the full joint distribution. So we're doing the right thing. Okay? Then let's say for a certain event you have a certain number of samples, then you would estimate the probability of that event as the number of samples consistent with the event divided by the total number of samples n. You can show from probability theory that if and your number of probability of an event in this way, however often it's true in the samples divided by the total number of samples, in the limit of infinitely many samples, you will converge to the right number. Any questions about this? Sorry, can you say that again?
Do you do all your sampling before you get any query, or do you use cascade variables before you sample?
Can you say that again?
Do you do all your sampling before you respond to any queries, or do you use the cascade variables and then sample after?
Okay, great question. So the question is, do you use the query while you're sampling? By the way, your question was clear from the beginning. I was just zoned out, not sure what was going on. We are about to get to that. How do you leverage the query to sample more efficiently? Let's look at an example of this in action. So here is a bunch of samples right here that we got from the statement. We have a query. We want to know the probability of W. For the probability distribution for W, you would count how many times plus W, that's 4. How many times negative W, that's 1. We normalize that, which makes it 0.8 and 0.2. Is that exact? Probably not after just 5 samples, but the more samples you get, the closer you will get. If you had a different query, let's say a conditional distribution query, you could do the same thing. So let's do that example. let's say the query were probability of plus S given plus R. We then look at all the plus R samples, which are the first 4. And in this case, half of them are plus S, half of them are negative S. So you'd end up with 0.5 as your estimate. Okay. One big point here is that the nice thing about sampling is that as you get your first or second sample, you can already make it sometimes at any time already. All the time you have to compute, you can just keep computing. Sometimes somebody cuts you off and say, based on the samples I have so far, here's the estimate. Rejection sampling. So let's try to make these algorithms, the first one we've seen so far, prior sample, a little more efficient by looking at the query ahead of time. Let's say you're interested in PC. Well, if you're sampling for PC, you can imagine that all you care about is the camera. All you need to know is plus C or negative C in a given sample, and that's just what you keep track of. So that's a small optimization you can do. Now let's say you want C given plus S. You're still interested in the C outcomes, but only the ones where S equals plus S. Now, if you are sampling, and you go from C to S, and then from there you go to R, and then to W, in that procedure, after S was sampled, continuing and sampling R and W is useless. It's useless to find a better answer to your query. We should already have a minus S. Whatever you sample for R and W is not going to make up for that, and it's never going to participate that sample in your answer to the probabilistic inference query here. So what would happen here is you would start sampling plus C minus S. We actually stop sampling and just throw this one out. Plus C plus S. This one you would potentially sample all the way. Minus C plus S, go all the way. Minus S, you would stop here and just never even see what's going on there. Same here, minus S, you would just have stopped and not continue sampling. And throw that sample out, because it's not going to help you. The ones that matter are these two over here, and based on those, you're going to answer the query. In this case, it would be P C given plus S equals 0.5. Yes? That's an additional optimization you can do. If you know that no variables appear further down below, you can even stop after this one here too. Good point. So there's 2 optimizations we can do. One is we can stop after we've seen all the variables we care about. The second one is once one of the variables we care about and is sitting in the evidence in the back here, and is sampled the wrong way, it doesn't even matter what's coming later, and we can already stop. So there are 2 separate optimizations here. Yes, so for this example here, that's most explicit. If you were to sample, in this case, R, and you already had plus C, let's say, and next you're going for R, plus C is this part of the table over here, you would say 0 to 1, the first 0.8 would be associated with plus R, and then the last 0.2 would be associated with minus R. You'd sample in the 0-1 interval, and then see where you land. And maybe another way to put it is, sampling is the foundational building block we have to do sampling. In a good random way. There's a lot of computer science. What does it mean? We assume that's the sample from distribution. The rejection sampling has two optimizations. One of them is once you've seen all the variables you care about, that is not correctly sampled according to what you need for your query, you stop running that sample. So here is your sample xi, still from xi given the parents. If you're not consistent with the evidence, you just reject it and you return. And as was noted up front here, I think the better way to put it is we go from I till nk, where nk is chosen such that all variables that you care about in your query have a number. So in this case here, t given plus s, t has index 1, s has index 2, so you only need to go up to index 2 and you can stop there to answer your query. Any questions? Sampling is better because we don't do the spurious computation, but it's a little bit not great because let's say you're sampling sampling, you're getting very lucky, not rejecting. Then the very bottom out of your basenet, and now, well, you sample all that work, sampling all the other. You say, oh, this sample is not useful to answer my evidence. In many of these nodes, travel with what you sample. Also, half the time, let's say in a 50-50 distribution, you get the wrong output. If you have, let's say, 10 variables with evidence, you have a very low chance of getting a sample out with rejection sampling once you have a lot of evidence. Okay? I'm going to skip over this. I'm going to go here. What we're going to do is, rather than sample every time you encounter an evidence variable, you're not going to sample, you can just go to this is for the query. What is the probability of a certain shape? Given color equals blue. And rather than just generating shapes and colors, these robots are always going to paint it blue. So you're forcing things to be blue, and you're hoping to make things still work out. So here's the problem that I just explained. Here's in the sampling example. You have 5 samples, only one of them has blue, and so 4 samples have been useless. Now let's say you can force it to be blue, then all your samples will be good. But the problem is not that because you are forcing the color to be blue, the sample will not be the right distribution would have a choice of colors and wouldn't always end up being blue. So the solution is that whenever you force a variable to take on a certain value, of it taking on that value, you account for that probability. So if blue was a very high probability, let's say 0.9, you just store that number with the sample 0.9. And you now have a weighted sample. If blue had a very low probability, and maybe 0.1 for a certain shape, store that number 0.1 with that sample. Now your samples are weighted according to how likely it was to generate that sample. So now when we generate samples, everything is blue here. No exceptions. That's just the way the procedure works. But we'll have to start weighting things. Now let's run an example here. We have a sample plus C plus S plus R plus W. This here was evidence and forced. This was evidence and forced. So the weight that we get for a sample like this, when we force it to take on particular values, we get a weight of, let's see, let me backtrack. Our query is P for something, which doesn't matter, given plus S plus W. For the procedure, it doesn't matter what sits over here. What matters is what's sitting in the back. So that's our query. We're going to force these to take on the values we want. Then we're going to start with a weight of each sample that's equal to 1, and then work our way through as we go through the sampling procedure. So first one, sample plus C or minus C. We have ended up sampling plus C. That was sampled, so no need to adjust the weight. Next variable, S. We would sample from this distribution over here, but we're forcing it. Since we're forcing it to be plus S, we need to account for the 0.1 here. At this point, we multiply our weight with 0.1. Next, we go to R. Parent variable C has the value plus C. So we have this table over here. R is not an evidence variable, so we just sample. Sample it, happen to get plus R. No action here, because we sampled it. So we don't need to adjust for weighting. It was done through the sampling procedure. And we go to the last one, W. We force it to be plus W. The parent instantiation is plus S plus R. Plus W has a weight here, 0.99, that we multiply in. That's our entire weight for this sample. It's in many ways the most intuitive thing you could do, right? Whenever you force something, you account for its probability and you just multiply them all together. Any questions about the procedure? Yes? Okay, that's a good question. Why? Since we know the query is about plus S plus W, why do we still need to put that weighting here? We'll see sketch of a proof on the next slide. But the intuition is that if you don't account for this here, when you force this to be plus S, you're not really following the distribution. You're completely ignoring it. And so you are getting samples that are not from the original distribution, but from something else. Yes? What is the? Oh, that's just a starting point. 1.0 is where we start, and then we multiply numbers in as we go along. Okay, here's the procedure. You step through your variables in order, consistent with the base net. If it's an evidence variable, you fix it to the observation value, and then set the weight equal to the current weight you have times the probability of that variable taking on that instantiation, given its parent's instantiation. If it's not an evidence variable, you sample it according to this distribution, just like we've done before. No update to the weights. What you return now is a sample with a weight. So what's going on here? If we look at the sampling distribution that we're working with, what's the probability here of sampling the evidence variables, which we'll call the ZI variables? Well, probability of sampling the ZI variables is, let me backtrack the notation. Z, unobserved, and E are the evidence variables. So we split our variables in two groups. SWS, the probability of generating a particular sample occurring when we sample with this particular procedure. What is the probability of generating a particular sample? Well, whenever we encounter an evidence variable, that evidence variable is just set. So that's always guaranteed. There's no probability involved there to make that happen. Whenever we encounter a variable that's not observed, we sample it from this distribution over here. So the probability of generating a particular sample is the product of the probabilities of generating each of the unobserved variables samples, which is given over here. So what we see is that the probability of generating a certain sample is not anymore the original distribution, it's a new distribution. It's a distribution that is this thing over here, where you only account for the conditional probability tables for the unobserved variables, not for the observed variables. We need to account for that. How do we counter that? Well, we now have weights. And the weights of a sample are the probability of the evidence variable EI, given its parent variables, multiplied together over all evidence variables. So what we see here is that in the weight of a sample, we keep track of the missing part of the distribution. This is what we account for with sampling, and this is what we account for with weighting. And multiplied together, they account for everything that's in the original full joint distribution. So multiplying together, we get everything from the full joint distribution. So what that says is that if we use our samples, empirical distribution that is correct for the original distribution. Actually, we didn't do an example, but for example, what you would have is you might have plus C, plus R, plus S, plus W, maybe with a weight of 0.2. You'd have plus C, minus R, plus S, plus W, maybe with a weight of 0.3. And then plus, maybe minus C this time, plus R, plus S, plus W, maybe a weight of 0.1. Now, if your query were probability of plus R given plus S plus W, you would say, okay, that's equal to, let's see how often where is plus S plus W? Everywhere, because we forced it. Plus R happens over here and over here. So this is equal to 0.2 plus 0.1 divided by the sum over all the weights, which is 0.2 plus 0.3 plus 0.1, which gives you 0.3 over 0.6, which is 0.5. So that's how you use these weighted. Okay, let's take a break here. And after the break, let's see what's still broken about this and look at our you'll get accurate answers to your queries. don't know how much time you're going to compute the answer. It has a lot of nice properties. First round, we saw the sampling of prior sampling. Prior sampling just samples, look for a lot of time in a basenet. There's two things not that great about that procedure. That means we're going to sample restart. You think about it. Subtract the probability of that parents, multiply them all together, and multiply our samples by the product of samples. Cases where there's you run the likelihood weighting for some, and it turns out that weighting you think about it. All right, let's see what people came up with. Anybody has any suggestions? Okay, so this is a great suggestion, and this really gets out. Let's say if a basement that looks like this. Very deep. And you have some evidence variable down here. And maybe there's a couple of those. And what that means is there's only one evidence variable, so you're just sampling everything top down. You land with these three variables over here. Let's say these are x1, x2, and x3. This one is maybe z. Then you're going to look at your CPT for z given x1, x2, x3. So look at e, z, x1, x3. Now it is possible that the values x1, x2, and x3 take on. Let's say for z you had plus as your evidence. It's possible the values x1, x2, and x3 take on. Make plus. You end up with a weight that's maybe 0.00001, which indicates that that sample is not going to contribute a whole lot to your computation. It's not a very useful. Procedure again. Maybe this was for plus x1 minus x2 plus x3. Try it again, and you end up with plus x1 minus x2 plus x3 again. Tough luck again, 0, 0, 0, 0, 1. Then you end up with something else, plus x1 minus x2 minus x3. And now the probability of plus z given this, plus z given plus x1 minus x2 minus x3, maybe is 0. So you just can't take on the plus z value with those values of the sample. What can happen is that which is your evidence. You only see the evidence once you get there and then weight it, but none of the work here accounts for the evidence. Ideally, you would have something where you say, I know it's plus z. I want x1 and x2 to be sampled in a way that they're very compatible. Imagine for something like this, you'd rather start from the bottom, fix plus z, and work your way up, right? For the evidence from the beginning, you get much better samples. This is how you do that, right? Because it could be a bunch of evidence variables in a couple of places, maybe some here, another one here, and really p plus z given x1, x2, x3 could be 0 always, except equal to 1 if minus x1 minus x2 minus x3. And so what that means is that sampling almost forever the prior. finding out about the evidence when it's too late. And GIP sampling will do that for us. Actually, before we go there, any questions about why likelihood weighting runs into trouble in these types of problems? Yes. Let's look at another example. Let's look at our coloring example. A little more, well, let's see. Let's look at an example with x1, x2, and z. Z is observed to be plus z. And you're interested in maybe probability for x1, x2, given plus z. Maybe the table here is 1 if minus x1 minus x2, 0 otherwise. The distribution for z. Now if you start sampling, your first sample comes around, maybe x1 and x2, you have plus x1 has a probability of 0.9, minus x1, probability of 0.1. Same here, plus x2, 0.9, and negative x2, 0.1. Now what that means, if you sample from this, it'll take a sample that has a probability of 1 over 100. So 1/10 of a chance here to get minus x1, 1/10 of a chance here. So if 1 over 100 probability that you sample minus x1 minus x2, in which case you'll get a weight of 1, and you'll see that that's a really likely outcome. And the other 99 out of 100 times you sample, you'll see that z is not compatible to be plus z. So on the average, you'll sample 50 times before you run into a sample that actually gives you any information about the query. That 1 out of 100. Question here.
I understand how the math works, but I don't quite understand like what it means to say that it doesn't give us any. Or I understand that you're like multiplying them, but I don't understand what it means to say it doesn't give you any information about plus z. Like,
Okay.
like
the weight.
cloud.
So let's say we have plus x1, plus x2, and then we set z to be plus z. The weight will be 0. We have plus x1 plus x2 again. Before it is plus z, the weight will be 0. Plus x1 minus x2 plus z, the weight will be 0. So when we compute with these weighted samples, how much they contribute to the final result is determined by the weight of the sample. And samples with weight 0 will not contribute at all. Samples with very low weight will contribute very little. So there's a gradual thing there. The lower the weight, the worse. Really, samples with very high weight. Those samples really help you answer your query.
Why did we keep getting the 0 one?
Just because we set it up such that plus z only happens if you have minus x1 and minus x2. Otherwise, plus z would never happen. So it's a special conditional probability table where it's almost always going to be minus z, but you just observe the evidence of plus z, and you're now wondering, what's my distribution for x1 and x2? You want to get that out. There's a question over there.
So the problem is, like, it takes lots of...
Absolutely. The problem is infinitely long. That's why. All of this. Okay. We just saw why likelihood weighting doesn't solve all of our problems. Why? Evidence influences the choice of downstream variables only, not the upstream variables. You want the influence of the evidence to go upstream so that it helps you sample in a more meaningful way, rather than sampling from the prior before you knew about that. The solution to that for us will be Gibbs sampling. And kind of the cartoon for that is very different. It's now not an assembly line where you can go to and then getting and the robot can keep checking things. Much longer. We're going to keep for a long time, and we're going to be reworking it. It's already going to come in with a particular shape and color. We're going to reshape it, recolor it, reshape it, recolor it until we say we've done it enough. And now here's a sample from your distribution. Okay, what's the procedure? You keep track of a full instantiation, x1 through xn. You can start with an arbitrary instantiation, as long as it's consistent with the evidence. But the evidence will always be consistent. Then you start cycling over your variables one at a time, and you compute condition on all the rest, the distribution for that variable. So say you have 4 variables. One of them was an evidence variable, let's say x4. You pick x1, x2, or x3. You say that's my variable right now, and I sample from x2 given whatever the other 3 are right now. That's a conditional distribution with one variable. Everything else is evidence. So it's a distribution with just one variable that you sample from. Compatible with the values all the other variables have, including compatible with the values of the evidence variables. Now, you started with an arbitrary instantiation. So after just doing this once, it's pretty much arbitrary. So you're going to keep repeating this. And the way to think of it is that these variables kind of become self-consistent. It's a lot like hill climbing, where you would say, when we saw you pick a variable, and you set it in a way that you minimize the number of conflicts, you pick another variable, minimize the number of conflicts. Really the same thing within a probability. You are picking a variable, and you're raising its value. Counting the number of conflicts, all the other variables are right now, and then sample from that distribution. Instead of going for, let's say, the most likely value given all the others, you go just for sampling. We want to generate a sample from the distribution. We don't want to generate the most likely instantiation of all of them. Okay, in the limit, if you do this infinitely many times, and under a couple of technical conditions, it will converge to the correct resample. You're going to sample from the right distribution. The nice thing here is that we incorporate upstream and downstream variables because we condition on all variables, including all variables. The contrast is exactly what we were getting at in the previous slide, is that likelihood weighting only accounts for evidence that came earlier in the basenet, not for the evidence that comes later. The consequence, we have these issues where you might have convert samples. The flip side is that we have now this local search where we cycle through all variables for a long time. We don't just pass through variables in one pass and be done. So let's look at an example. Let's say you're interested in probability for variable S, the distribution for S, given the evidence equals plus R. So first step is fix the evidence. R equals plus R. Second step is we initialize other variables randomly. Doesn't matter how you do it. Maybe you could run likelihood weighting. Who knows what you want to do? You initialize it in some way. Here's our initialization. This is not a good sample. This was just randomly generated and not in a good random way. Just random in an arbitrary way. Then step 3 is to repeat this process over and over of picking a variable, just like in hill climbing. You choose a non-evidence variable. Why? Because the evidence variables have to stay fixed to whatever the evidence is. R we can never change to anything else than plus R. So pick a non-evidence variable, X. In this case, we pick S. We uninstantiate it. And now in this basenet here, we compute the conditional distribution of S given all other variables instantiated. We sample from that distribution. And after sampling, we got plus S. Then we pick a new variable, in this case C. It doesn't have to be C, you just cycle through them randomly. Pick C, compute the conditional distribution of C given plus S plus R negative W. Sample from that, and instantiate C again. C became plus again, that's fine. It doesn't have to change. It's sampled. Whatever your sampling value tells you it to be, it's what it's going to be. We pick W now. Same thing, compute the conditional for W given all the other variables current instantiation, and then sample from that. And you keep going, and this is important. On the slide, we could only fit each variable once, but you have to keep going in this procedure many, many times. Now the question that remains is, and when I say resample a variable, can we do that efficiently? Let's say we resample from F given plus C plus R minus W. That's a probabilistic inference query again. Probabilistic inference is not always do it efficiently. But whenever you have a query where all variables but one are instantiated, you can answer that query very efficiently. So we're going to find this distribution. Look at the computation here. This is just using the definition. Now, after we use the definition, we write this out more explicitly in terms of what it looks like for the base net. Right? The base net says that this distribution factors as follows. What we have right here. Then we say, well, summing over S, sure, that's like variable elimination. We know that we should group all the terms that have S in it, push those to the back, and put the sum over S in the back with them. That's happening over here. Now what are we left with? Let's look at this fraction here, P plus C, plus R given plus C, plus R given plus C. So we're left with this expression over here. That expression allows us to compute the conditional distribution of S given all its evidence variables. If you carefully look at what's happening here, in any given basenet, only very few variables will replace the expression. Most of them will have canceled out over here. Which ones were we able to cancel out over here? All the ones that had a conditional probability table that did not have all conditional probability tables, if S doesn't appear, it would have canceled out. So this expression here, the number of conditional probability tables you're working with is for variable S. Look at it, well, it has its distribution given its parents, that's one distribution. Then it has for every child that it has another conditional probability. 1 plus the number of children that S has is the number of conditional probability tables that participate. The number of variables here, the only variable that really appears is S. So even though we might have the number of children plus 1 tables that we need to look into, for almost all of them we just need to look at, there's only one variable in them which is S, all the other entries are fixed. That's what you do for resampling. So this resampling can be done very efficiently. Okay, if you want to read a little more, Gibbs sampling produces samples from the query distribution in the limit of sampling infinitely often. Now, Gibbs sampling is something that's part of a more general called Markov chain Monte-Carlo methods. These are methods where you sample based on, you keep resampling your variables in principle infinitely often, and you somehow converge to the right distribution, a sample from the right distribution. If you do read more, you run into Monte Carlo methods. Monte Carlo, that's a casino down in Monaco, that's where it comes from. But really what it is, in the context of books on this topic, is sampling method. So just a different name for saying sampling methods. So today we've seen many Monte Carlo methods. In summary, what have we seen? We've seen prior sampling. We have seen rejection sampling, which cuts out some work from prior sampling. We have seen likelihood weighting, which forces the evidence to be right, which is typically needed when you have a lot of evidence variables. And then we have seen Gibbs sampling, which knows how to account for the evidence when sampling all variables rather than just the downstream variables. But the price you pay is like all the variables, principal infinitely long, so we get a sample from the right distribution. Okay, that's it for today. Thanks.